All right, well, hopefully this will be the last video with parallel plate type stuff for you guys. I'm going to show you one last little couple sets of little tiny little things here with parallel plates are kind of neat. Here we've got a parallel plate, so we've got a proton, electron inside of them. The proton goes towards the right with the field. The electron would go against the field towards the left. And let's say there is 1 volt of potential difference between the plates. So not very much, just a little bit. Now, the amount of work and energy to go across, the energy or the work done, whatever you want to call it, the energy, the work, blah, 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 kinetic energy, whatever, for both of them would be equal to Q times V. And they would have the exact same kinetic energy, exact same work done, the exact same everything, because it's the same voltage. They have the same charge, it makes no difference. And if we would put the charge of the electron or proton in for Q and we multiplied it by the 1 volt, I know that's tough multiplication for you guys, that would be like 1.6 times 10 to the negative 19 joules in order for it to go across. And this right here, this is actually the basis for an energy unit that's actually used really well. It's quite common with subatomic type stuff and fields and stuff like that. This is what is called 1 electron volt, or EV. And it's the idea is, how much energy you would take to take an electron or a proton. Okay, I guess the name is sort of referring to electron. How much energy you would take to go across 1 volt of potential difference. And it's called an electron volt. And if you haven't noticed, like all the energies we have are very, 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 very small, really small exponents. So using electron volts is actually a lot easier to compare and relate stuff to. And it's actually a really simple type of calculation. It's just a unit conversion for energy. And it's how much energy is required for an electron or proton to go across 1 volt. And using this can be really handy. For example, suppose you had a 1500 volt potential difference. Well, if you have 1500 volts and you're using an electron or a proton, that tells you right there that the energy would be 1500 electron volts. It's just that easy. It's a lot. You don't have to do Q times V or QED or 1 FMV squared. It tells you exactly what the energy is going to be as long as you're using an electron or a proton. If you had 1 trillion volts of potential difference, well, then the energy would be equal to 1 trillion. Like it's just that easy. So using electron volts is a really, really simple thing to use when they're doing subatomic energies. And you look at atomic stuff, whatever, you'll see electron volts used all the time. Okay, and it's a really, really simple idea. If you've got here, let's say you've got let's say you got 4 electron volts. How many joules would that be? Well, 1 electron volt is just 1.6 times 10 to the negative 19. So he's going to multiply that by 4, and 4 times 1.6 is going to give you, that'd be 6.4 times 10 to the negative 19 joules. And the exact same thing can be done if going back and forth. If you've got the number of joules, suppose you've got 7.2 times 10 to the negative 12 joules, and you want that in electron volts. So you just take the 7.2 to the power of negative 12, and you divide that by basically the charge of electron or proton, or 1.6 negative 19 joules per electron volt. Divide the two out, and you will get about 4.5 times 10 to the 7 electron volts. And it's really, really common to use prefixes with electron volts. So this would be 45 mega electron volts. So it's just a basic conversion factor back and forth between energy and electron volts in terms of joules and electron volts, and it's really, really common for you to see it. So, and you can take any energy you want. Suppose there's just a proton. So here's my little proton. Okay, my proton's flying at 3.4 times 10 to the 7 meters per second, and I want to know its kinetic energy in electron volts. Well, just find its kinetic energy the same old way you've done before, do the 1/2 mv squared, and calculate the kinetic energy. and we get about 9.65 times 10 to the negative 13 joules. And then if we want to convert that into electron volts, we just divide by the 1.6 negative 19 value, and we can find how many electron volts, and that would be 6.03 mega electron volts. So really, between joules and electron volts, it's more of a like an accessory calculation for you guys. If you get your answer in joules, you can change it back to electron volts, or you got information electron volts, go back to joules. All your formulas use joules, so it's really a conversion at the beginning of the question to get into joules, or maybe a conversion at the end of the question to put into electron volts, and that's about it. But it's a really simple idea, really simple calculation, and you'll see the electron volts a lot in chemistry and physics when you're dealing with subatomic stuff and atoms. It's actually, it's all over the place. So that's the basic idea behind electron volts, and converting back and forth is relatively simple. And again, it's all about, protons, electrons flying across 1 volt. That's where the idea came from, and it works really simple. Okay. Okay, well now let me show you one other little thing that I think is pretty cool about this type of stuff. And here we've got a parallel plates, obviously. You got the positive plate, and you got the negative plate, and inside here we're going to put a Q, and the Q is going to go flying across, blah, blah, blah. Now, when the Q actually flies across, of course, there's energy involved, and that can be Q times V, which could turn into like 1/2 mv squared, blah, blah, blah. We've done this type of thing before. And just by doing that's kind of cool, because you can actually see that how fast the actual charge will end up going depends on the Q value as well as the voltage. It has nothing to do with how far it actually goes, because if these plates are hooked up to 100 volts, the charge doesn't change. It then dictates how fast it's going. So you could actually take the plates and move them apart, and you could take this plate and move it way over here, and it would still hit with the exact same speed because you haven't changed the charge and you haven't changed the V. It would hit with the exact same speed it would if the plate was really, really close, even super close. It makes no difference where you put the plate. As long as you know the voltage, you can calculate exactly how fast and how much energy there's actually going to be in the situation. And that's one of the huge advantages of using electric potential and voltage to figure stuff like this out. It works really nicely. You could have the plates a few centimeters apart. You could take this other plate and you could put it on the moon and it wouldn't make any difference. That charge is going to hit with the exact same speed. Now, of course, when the plates are really, really, really far apart, it seems kind of weird that it would hit with the exact same speed. But if the plates are really, really, really far apart, and if we go back to the expression, the electric field is equal to V divided by D, if you move the plates really, really far apart, the electric field will get really weak. The voltage stays the same, but the electric field would get really, really weak. So if the electric field gets weak, you're going to have a very, very weak force, which means you're going to have a very, very weak or low acceleration. So it's going to take a lot longer and it's got to go a lot farther, but it'll end up hitting the exact same speed as it would if the plate was really, really close. I always thought this was kind of neat. So it's not really about how far it goes. It's not really about that type of stuff. It's all about the potential. The electric potential actually dictates how fast it ends up going. It's really kind of cool. So that's one of my other favorite things about this type of stuff is it's all about the potential, and having that voltage is really, really handy. I love the QV equals 1/2 mv squared type connection to calculate how fast charges are going. I think it works really, really well. But that's just one of my other favorite things about it. And that's why I love electronic stuff, and whether it's in computers or on even just on a battery or cell, the plug, that's why voltage is one of the most common measurements to get in anything electronic, because the voltage dictates pretty much everything. Regardless of the length of the pathway, it dictates pretty much everything that goes on inside the circuit and how much energy the charges actually have to work with. So let's see if we can apply a couple of these ideas, sort of link things together a little bit to show how it works. Let's get rid of this Q value in here, that type of thing. Let's move this back over here. All right. Okay. So let's just make something up here. Let's use an electron. electron goes flying across. Of course, it will go to the left. It flies across and it hits the other side. And let's say it hits with 148 electron volts of kinetic energy. And I want to know how fast was it going? So how fast is it going when it hits on this side, and what is the potential difference between the plates? Now, this is relatively simple, no big deal. And now just keep in mind, it's kind of like we were talking before, we don't need a D for anything because the distance has absolutely nothing to do with this. If I wanted the electric field, I need to know the distance, but I'm not interested in the electric field. I'm just trying to find out what the speed was and the voltage that was used to actually do this. Now, I can use a lot of this idea right here. Now, first things first, I've got electron volts, so I'm going to change that electron volts into joules. That's the first thing I'm going to do. So I got 148 electron volts, and I'm going to convert that into joules because all of our stuff that we use is in joules. So this would be about 2.36 times 10 to the negative 17 joules. And you can sort of see why people like electron volts, because 148 is a lot easier to visualize than 2.36 to the negative 17. Okay, now that I've got this, that is my energy. So there's my energy right there. And this is the energy for everything. So here's my energy that was used. And I can use this as my work. I can use this as my potential energy. I can use it for whatever I want. It doesn't make any difference. That's the energy involved. So if I would take this, I can take that 2.36 negative 17, I can take that and I can make that equal to my kinetic energy, and then I can use that to solve for how fast it was going. Okay, so I put in the 2.36 negative 17, and I times by 2 divided by the mass of the electron, get the V, don't forget to square root for the V, and I can calculate how fast it was going. And if I do that, I find it was going 7.2 times 10 to the 6 meters per second. Okay, so that's how fast it was going. Now if I want the voltage, that 2.36 negative 17, this is also the potential energy, which a lot of people just use Q times V to solve for. And I can solve for my voltage with this. I can solve for my potential difference. Just take that 2.36 negative 17 and divide it by the charge of an electron, and I've got the voltage that was used. Now, the thing is, if I do that, that's going to be my 148. That's one of the advantages of using electron volts. I know my voltage is going to be 148 volts. And you just calculate it. Take the 2.36 negative 17, divide it by the charge of the electron, you're going to get 148. I mean, that's where we got it from in the first place. Now, of course, if it's not an electron, not a proton, then you'd actually have to divide by the actual charge of the nucleus or the charged object, whatever it happens to be. But this one conveniently is an electron, so it makes the calculation a lot easier. So this is sort of how your electron volts kicks in a little bit. This is showing that the distance has absolutely nothing to do with how fast it actually goes. It's really the advantages of using electron volts compared to joules in terms of making certain calculations a lot easier, like a basic energy calculation.